Today our focus is going to be on increasing, decreasing, and constant. So there are three things that a function can do. It can rise, it can fall, or it can remain the same. Would you agree? Okay. There's really no other option, right? Okay. So what I want to talk about is what this has to do with the derivative. And you already kind of know a little bit about what this has to do with the derivative. Okay. So I'm going to show you a picture of what each of these look like. And you and your group need to decide what it means about the derivative. Here is a picture of a function that is increasing. Decide at your table, what does that mean about the derivative? Okay, everyone say together, what does it mean about our derivative? What does it mean about the derivative? It's positive. If our function is increasing, then we know our derivative is positive. That's something we talked about in Unit 2, correct?
Yes.
Okay, so let's try this again. If our function is decreasing, what does that mean about our derivative?
Negative.
Okay, if we are decreasing, our derivative is negative. Talk to your group about this. If we have a function that is constant, what does it mean about the derivative on that interval?
Oh, I didn't feel it. The next
Show
one.
me with your hands. What does it mean about the derivative? It is 0.
I bet the next one's a flipper.
As a pod, I want you to tell me when our function is increasing, decreasing, or constant.
In that order. Oh wait, no, we're decreasing in the middle.
It's increasing, you're making
Yeah, that's what I said. It's decreasing from 3 to 5, so 1 to 3, 1 to 3. Well, I said it in order, that's all. Oh, it's from 1 to 3. Born. And then 3 to 3.
It's 5.
Is it 5?
It's 5.
Okay.
Pod 5, when is our function increasing?
From -3 to 1. With the,
What?
oh, I was gonna say brackets.
Well, would you say that at 1 it is increasing? Okay, I would not say that. We're always going to use open parentheses because at those points it's like switching directions or changing, and so like you don't want to include one in increasing but then also include it in the next one. You see what I'm saying? So we're never going to include the endpoints. Pod 2, decreasing.
3 to 5.
Pod 4, constant.
1 to 3.
Are they correct? Yeah. I was looking at all of them were in your head. Okay. We're going to use open intervals because at a point where we're changing directions, we can't really say it's increasing or decreasing. Okay? Now, if you think back to yesterday, okay? When does this change from increasing to decreasing and vice versa? Okay. And what's true about the derivative at those changes in direction? Or?
Or undefined.
Or undefined. Okay? So our critical points are still going to help us figure out where we have potential relative minimums and relative maximums. And those relative minimums and maximums are where we have changes in direction. Okay? So, if I give you a function and I ask you to tell me where it is increasing or decreasing, this is what you are going to do. You are going to first find the critical numbers, because those are possible points where we're going to change directions. Okay? You are then going to draw a number line with your critical points. Maybe it looks like that. Okay. Our critical points are the only times where we could switch directions. And so what we're going to do is we're going to test the intervals that our critical points break our number line up into. Okay? So we're going to test points to figure out where is our derivative positive, where is our derivative negative. If our derivative is positive on an interval, we know that our function is increasing on that interval. If our derivative is negative, we know that our function is decreasing on that interval. In order to find critical points, what do we need? In order to find critical points, what do we need? The derivative, okay? Anytime I ask you something about increasing and decreasing, in your mind it should register that we need to look at the first derivative, okay? Have a wonderful day. First example, very nice cubic function. F of x is x cubed minus 12x minus 5. And I want to know where this function is increasing and decreasing. Okay. So, following the 4 steps on that previous slide, first one we need to find critical points. In order to find critical points, we need our derivative. Aaron, what's our derivative?
3x squared minus 4.
Okay. In order to find critical points, we need to know where this is 0 or undefined. Will this derivative ever be undefined? No, it's not a fraction, so we don't need to worry about that. So let's set it equal to 0. Some of you are already working ahead of me, aren't you?
Yep, I've already done the number.
Okay. When is this equal to 0? So we're going to draw a number line, and I always like to label my number line. Since we're using the first derivative, I'm going to write f prime. Okay, that way when we get into using the second derivative, we're going to have 2 number lines potentially. So it's good right now to just practice labeling it. Okay, so our critical values are -2 and +2. Okay, we're going to pick x values in each of these intervals to figure out if our derivative is positive or negative. So what is a number in this interval right here? -3. And if we plug in -3, we have 3 times -3 squared minus 12. Is that a positive or negative number? Positive. I don't care what the value is. We only care that it's positive. And all of the numbers in this interval will have a positive value for the derivative. Okay. Between -2 and 2, what could we plug in? 0. If we plug 0 into our derivative, is it positive or negative? It is negative. And so are all of the other x values when we plug them into the derivative between -2 and 2. All right, after 2, what's a nice number to plug in?
10.
Sure. It actually, because 10 squared is 100 times 3 minus 12, is it a positive or negative number? Okay. Now, since this is our first derivative number line, we tested these numbers in our first derivative. Okay. Now, since our derivative is positive here and it's positive here, what does that mean about our function? It is increasing. So we can say that our function is increasing from -infinity to -2 and 2 to infinity. If our derivative is negative between -2 and 2, what does that mean about our function? It's decreasing. So our function is decreasing from -2 to 2. That is all we're doing today, people. What'd you say there, Josh? It is, isn't it? Okay. Now, I will tell you, the most challenging part of this is not the calculus. It's the algebra when you have to solve. Okay? So let's work on one that's not quite as straightforward. Ladies and gentlemen, please write this problem down. Okay, we are asked to find increasing and decreasing intervals. We know we need critical points. Please find me the derivative. When you have a derivative, simplify it and then compare it to your neighbors. Q, what is your initial derivative, like before you simplified it?
2/3 times x squared minus 9 to the -1/3 power times 2.
Okay, do you agree with Q's initial derivative? Okay, this is something that we did yesterday and I didn't really tell you why, okay? Anytime there is a negative exponent, I need you to rewrite it to be positive, okay? So that means you need to move it across the fraction bar, okay? The reason I need you to do that is so you can visually see if you have something in your denominator or not, okay? I didn't do a very good job of telling you about the negative exponents. We just kind of did it yesterday, all right? So if you have negative exponents, move them down across the fraction bar so that you have a fraction, and that's easier for when you're determining when you have 0 and undefined values, okay? So, how did you simplify this, Q? Or did you?
I ended up with 4x over 3 times x squared minus 9 squared.
That is perfect. Any questions how we got there? Two x times 2 is 4x. The 3 is in the denominator. The negative exponent goes to the denominator. Okay? So we need critical values. Since we have a fraction, we need to consider where our derivative is 0 and undefined. Okay, so Abram, what do we do for our derivative being 0?
Just the numerator equals
So when's our numerator equal to 0?
0.
Great. Okay, Michael, if we want an undefined derivative, what do we need to do? When is our denominator equal to 0? Plus or minus 3. Okay, so I'm going to draw a number line. We have 3 critical values. Okay, we have 4 intervals to test. Keep in mind that it doesn't matter what the actual value is. It just matters if it's positive or negative. Okay, so sometimes when I plug in to test intervals, I don't actually figure out the number. I just say, okay, this is going to be positive, this is going to be negative. If we divide a positive and a negative, we have a negative. That kind of thing. So, how about this? 1, 2. We'll do it together. What is a good number to plug in between negative infinity and negative 3? Negative 4 sounds great. If we plug in negative 4, that's going to make our numerator negative. What about our denominator? Positive. So we have a negative divided by a positive. That interval is negative. Between negative 3 and 0.
0.
We can't pick 0.
No, sorry.
Okay, 0 is a lovely number to plug in, but since it's a critical point, we cannot. So if we plug in negative 1, we'll have negative 4 over. This would become negative, right? And a cubed root of a negative is a negative. So we have negative divided by negative. That interval is positive. You will not have a calculator when you're doing this. Okay? That's why we're not plugging away at this. Okay, if we plug in 1, we have a positive 4 over 1 minus 9 is going to be negative. The cubed root of negative is still a negative. So we have a positive 4 over a negative number. So when we divide that, it would be a negative value. That interval is negative. And if we plug in something from here like 4, we have 16 over 3 times the cubed root of 16 minus 9. That's going to be positive. Our function is increasing from negative, it is increasing from negative 3 to 0 and 3 to infinity, since that's where our derivative is positive. And we are decreasing from negative infinity to negative 3, and 0 to 3, since that's where our derivative is negative. Favorite.
Will the number line, will that always just transition from negative to positive?
I'm really glad you asked that question, okay? There will be a lot of times where it will just switch back and forth from positive to negative, but that's not always the case, and so we cannot assume it, okay? Yes.
Do we always have to have that V or U or whatever between them?
I just like to union my intervals together so I know that they go together. If you don't, I'm not going to get upset. That's just a notation thing that I like, and that, like, that's what I teach in pre-calc, okay? And you didn't have me for pre-calc, so it's great. Yes.
How do we write it if it's constant? Like, that just says it was increasing and decreasing, or it's just.
So I'll tell you what, the only time you're going to get a constant is if you have a horizontal line, or if if we have a piecewise function. And so if that's the case, you would probably be identifying it from a graph. Okay. Now I want to come back to Abram's question. Okay. Let's think of the graph x, or let's think of the function x cubed. Okay. What's the derivative of x cubed? 2x squared. And where is that derivative 0? What? 0. If we make a number line with our critical number, if we plug in a number over here, what's our derivative?
Oh,
Right? Negative 1 squared is positive. If we plug in a number over here, it's going to be positive. We don't necessarily switch from negative to positive and vice versa. Most of the time, yeah, you'll see that, but not always. Now, I do want to tell you that this function is not increasing from negative infinity to infinity. Because is it increasing at 0? No, our derivative is 0 at 0. So you would have to write this as negative infinity to 0, 0 to infinity. Okay. Thank you for asking that. Any other questions? Okay. Here's our next one. And our last review. Oh my goodness, day 35. Ooh, our last example.
is that 4?
That is a 4. That's x to the 4th plus 1 over x squared. My projector's a little off, it looks like. Maybe my pen can't fix it.
Yeah.
I just can do it. It's not better. Okay. We're going to have to find the derivative. I would like you to find the derivative and simplify it the best that you can. We can't figure out critical points unless our derivative is simplified. Okay. 30 seconds. I have my initial quotient rule up here, but in 30 seconds I'm going to ask for your simplified proof. All right, Logan, what is your simplified derivative?
2x to the fifth minus 2x over x to the fourth.
Do you agree with that? Yeah? Okay, what I would probably do, I would factor out a 2 and an x from the numerator. And technically, you could reduce this by an x. Do you agree? If you didn't reduce it by an x, you're still going to get the same critical point. It's not going to be a huge deal, but that is a possibility. Okay? So we need where our derivative is 0, and since we have a fraction, we also need to consider where it is undefined. Now, our numerator is what we focus on for our derivative being 0. X to the fourth minus 1 equals 0. X to the fourth equals 1. When does that happen? Plus or minus 1. Okay, if we fourth root, it has the same effect as when we square root both sides. Okay, we still have a positive and a negative answer. Okay, so how about this, Colesmith? And I feel like you just forgot it. You could look at this as x squared minus 1 times x squared plus 1. Okay. When is our derivative undefined? When our denominator equals 0, so x equals 0. That's why I said your number line wasn't clear. All right, go ahead and test your intervals for me, please. Now that we agree on critical points.
I got you. All that's positive.
There's only 30.
Cool. I will do. I'll do one. One half.
She gave me.
One half is positive, negative one. Negative one half is negative. Yeah, so it's.
Well, I'm not gonna figure it because like all of it like that's not.
Okay, now? Yeah, it's great. Oh, yeah.
My sister's like, okay.
It doesn't like.
Wow, I thought you said you counted.
No calculator. No calculator.
I'm gonna show you what the graph looks like.
Oh,
okay.
Okay. Is this interval positive or negative? It's positive?
Negative.
It's negative?
negative over, yes, it's a negative over a positive. Same thing though.
I have a negative. This interval. This interval. Okay, any issues with getting those? Okay, remember you don't actually have to figure out the value, you just have to figure out if it's positive or negative. So, our function is increasing from -1 to 0 and 1 to infinity. Our function is decreasing from -infinity to -1 and 0 to 1.
That was negative half.
You would like to, you're contesting that?
Well, x to the fourth, that's gonna be a positive number.
Okay, what are we plugging in? Positive 1/2?
Negative one half.
Negative 1/2. Okay. Well, negative 1/2 to the fourth is going to be a fraction. Minus 1 is going to be a negative number. Negative 1/2 cubed would also be a negative number.
You didn't even like say right. It turned out to be wrong.
Okay, so I wanted to show you the graph of this. What was our original function?
X to the 4 plus 1 over x squared.
Over x squared?
Yeah.
That is our graph. Decreasing, increasing, decreasing, increasing. We have a vertical asymptote at x equals 0, which is why we got an undefined value for our derivative. Okay. We'll get into more of like the asymptotes and corners, which are which, next week. But for now, we've identified them as critical points. But does that graph match our description? It sure does. Okay. So on your gold sheet, you will find your homework, these problems. It is 8:45. I challenge you to do at least one problem before you leave, if not two.
Are you